So I'm happy to be here and to see a lot of international people, because last year I was in Vienna, because everybody says that, and we were mainly between French and Austrian people, and it was fun. We have been welcomed at the airport by the army, but so it was interesting, you know. So now things are changing, and I think it's pretty good. So the goal of my talk is to try to answer to the question, which is I'm able to solve the TSP, and I want to solve it with a 100-core machine. So I have a 100-core machine now in my office. So I have a free heater, you know. So that's interesting. And so I'm going to speak a little bit about CP and more about parallelization. And so the CP model that we have currently to solve the TSP mainly comes from the PhD thesis of Nicolas, who is the co-author of this paper. And the model is based, I'm not going to give so many details except for this thing, which is really problematic for the TSP in parallel. So we have a weighted circuit constraint, which is based on a Lagrangian relaxation of the one-tree. We have K-custom constraints, which are constraints that are structural constraints, meaning that if you split your graph into two parts, and then if you want a cycle at the end, you need to go through an even number of edges between the two parts, okay? So this is the idea. We have some things that we call mandatory Hamiltonian path constraint, which just means that if you search for an optimality, when you have a subpath, your subpath must be optimal. That is, it's not possible to have a rearrangement of this subpath which conduce to a lower cost for the subpath. And so we mix all the things together with a search which is particular, and I'm going to give some details about this search. So if we do that, currently we are competitive with Concord up to 200 nodes, which is not bad, and we are sometimes competitive up to 500 nodes. And what is interesting is that there are some things that we don't see, and which explain why it's difficult to be really competitive. But if your graph is not too big, so now we have a good solution. So here, when you want to parallel the search for solution, you have different solutions. Here is a simple one, and I'm going mainly to discuss about embarrassingly parallel search. The simple thing is you can imagine you have K workers, and the idea is that you want to use these K workers. The first solution is to split your problem into K parts, okay? And then you give one part to each worker, and you expect that it's going to work. And for some problem, it works. For instance, for the n-queen problems, that works pretty well to do that. Often, unfortunately, the results are not good, and this does not scale up. The scaling is really an issue in parallelism. And so the idea of embarrassingly parallel search is to start from the fact that the static decomposition is simple, but it's very difficult to split into equal parts. So the idea is to split into a huge number of parts and then to give that part to workers. And so in order to hope that the sum of the resolution time will be well balanced. Okay, what is important is that it's not to have equivalent problem, is that the workers spend equivalent time in solving the problem. Okay, this is something that is very, very important in parallelism. So if we look at embarrassingly parallel search, we have two steps. One step, which is called the decomposition, in which we are going to decompose my problem into a certain number of sub-problems. And we want that sub-problem to be consistent with the propagation. That is, when we run the propagation on this sub-problem, we don't detect any failure. So why we want to do that? Because there is a rules in parallelism which say that you have to avoid to do in parallel what you will not do in sequential, okay? And so the decomposition is that your sub-problem have to be consistent, like if you did that in a sequential process. We put all these sub-problems into a queue, so this is static, and then we have a solving process. When a worker needs some work, it takes a sub-problem from the queue and solves the problem. And this is dynamic. So we have important thing about EPS. The first is that we consider, this is an assumption, that solving independently two divisions of some part of a problem must not be longer than solving the whole part, the whole problem. So This is usually not really true in MIP, and this is not really true with some learning process that we can have, and we are going to see that with LCFirst. So the second thing is that we consider a specific problem here, which is the TSP, and for the TSP, we have very good heuristic. Okay, it means that Lin-Kernighan heuristic gives boundaries that are very close to the optimal value. So in fact, our problem is not really an optimization problem. It's much more a satisfaction problem, even if it's not exactly a satisfaction problem. And from that fact, Louis Martin, Rousseau, and I think Jean-Guillaume and Xavier Lorca propose a strategy which is interesting, which is LCFirst, that I'm going to develop in 2 slides. So, and the idea is that a good number of subproblems per worker is between 30 and 300. So if you have 10 workers, so 10 cores, you split, for instance, in 1,000 parts, okay? So does it work? So what's the idea in general is that the main problem with EPS and the TSP is that EPS is based on the decomposition, and the decomposition is a breadth-first process. That is, roughly you select a subset of variables and you compute all the partial solution for this subset of variables. It's going to give you a number of subproblems. So you have your subproblem. But the strategy which is very efficient for the TSP is a very specific one. That is, this is LCFirst strategy. It selects one node from the graph according to a heuristic and keep branching on the node until there is no more candidate, no more edges around that node, no matter if we backtrack or not. That means that we are going to discover some nodes, some LCFirst node, and we want to assign edges around this node, and this node can go up in the search. And the problem is that this is a depth-first process, and it contradicts the breadth-first process of the decomposition. So what does that happen exactly? Imagine here we have a search. Here we select the node A, and so we are going to try to assign edges around A. So we just have to assign 2 edges, because so we assign AB here, and then we assign AC here. Okay, that's finished. A is finished. So we select a number node D, and we try DE, it failed. We remove DE, it's failed again. Okay, so now we go back, but when we arrive here, we don't change the LCFirst node. We keep that node, okay? And here we say that we no longer want AC, but here we continue to select node edges according to the node D, okay? And so we repeat that, and you can see that now E is going up into the search. And so this strategy is really efficient. It's really annoying to have a so much efficient strategy which has a so strange behavior. So the problem now, imagine that you are doing EPS, and so you want to do a breadth-first thing, and so you cut the search here. So normally, if I repeat the search here, the problem is that here I should have D as the first node. And the problem is that I don't have D here, I have E. And so here, if my depth is not a lot, the problem is that I'm going to be very different from LCFirst. And so the results, honestly, are very different. And the results are bad in parallelism because your decomposition is not very good. So this is why we propose something at CP2 2020, is that, in fact, we are going to try to learn a little bit what LCFirst is doing. That is, we are going to send some searches, and then with a number of backtrack, we run them and we try to extract key information from LCFirst. We don't need to be exact, we just need to have a kind of idea of what LC search will do. And so we are going to use that during the decomposition of EPS in order to have a better decomposition. Almost a linear gain on the number of cores is obtained. The number of backtrack performed is considerably reduced. Without this method, it's possible to observe a degradation of performance according to the number of cores. Don't worry, you will see that even with this method, we can also observe a degradation of performance. And we are going to see that in a few minutes. So, but if we do that, for instance, we obtain very good results for 4 cores. Okay, but when you want to do some parallelism, and when you speak with people doing some parallelism, and for instance, I remember that I gave a talk to Huawei, to a group of parallelism in Huawei, and they just asked me one question. Well, what's happened when you have 100 cores? Okay, this is the immediate question. And you say, oh, what's happened? I have 4 cores, it works well. I have 8 cores, it works well. 16 cores, that's very good. Look at my graph, this is very good. And so the problem, some problems appear more strongly. This is the thing we are going to see. So we can identify 3: unstable decomposition, non-monotonic decomposition, extremely heterogeneous subproblems. So if we look at that, unstable decomposition, it means that when I decompose more, suddenly I can observe that I have a degradation of the result. The problem is that when I involve more worker, the number of subproblems per worker does not change, so it increases the number of global subproblems. So when I involve more worker, then I increase my number of global subproblems to do, so I have to decompose more. And so this is the first thing that happens. Is that, for instance, when I consider this problem, when the problem of the TSP lib, there is a type of problem, and this is the number of nodes of the problem. The problems are complete. The graphs are complete. So here it needs sometimes, as you can see, this is not in milliseconds here. Huh? We speak that are problem. Huh? So 90,000 seconds to be solved sequentially. You took EPS, you take, you consider a number of subproblems per worker of 30. It requires 10,000 seconds, so this is not bad. With 24 workers, why it continue with 48 workers, so you are good. A little problem here, and not better here. Okay, so the problem now, and then you can continue if you want, you can simulate, and sometimes you are going to go up. And so you begin to understand why there's what happened when you have 100 cores. Your curve is doing that. So this is the second point, is that the second point, which is very strange, is that you imagine that you are going to decompose your problem. So you make a kind of breadth-first decomposition method, and then the number of subproblems should always increase. No. Okay, that sometimes it begins to decrease strongly and then re-increase, then re-decrease. And so you have to manage that. And you can see that. So this is not really pleasant because you need to make a more complex process. And then suddenly we have another thing that appears for 100 cores, is that a very small number of subproblems can take a very large part of the overall solving time. For instance, if we consider this one, okay, then and we decompose in 300 subproblems, only 5 subproblems takes 50% of the solving time. Okay, but now it's become a problem because when you have 4 cores, the minimum of usage is 1 core over 4, that is 25%. Okay, but when I have 100 cores, and at the end there is only 5 workers which works, so it means that 95% of my workers are lost. Okay, and so my power is going to be inefficient. And so this is independent of the number of high-level work. So the idea to do that, we propose to reduce the number of subproblems that are considered during the decomposition and to be prepared to redecompose. And if needed, we repeat the process. So the problem is that if we do that, the question is when should we recompose, under which condition? When a worker is aborted, it's not already performed some computation. How can we avoid redoing some computation that has just been done? We have questions like that, and we are going to try to answer to this question. Okay, so the first idea is that we don't want to decompose too much because we don't want to have bad effect of the decomposition. But the problem is that if we decompose less, because we are prepared to redecompose, if we decompose less, we are going to have a bad load balance. Okay, because this was the reason for which we decompose more. So, but when there are 100 workers, less important to have 2, 5, or 10 workers that are not active when you have only 4. Okay, So the things are different, and this is why so many things are changing when you have 100 work. And the second thing is that if we have extremely heterogeneous sub-problem, de facto, we are going to have a bad load balancing for solving that problem. So breaking that problem later will be fine. The problem is that we don't know what are these sub-problems. Otherwise, we could decide to break them immediately. So we have to do that while satisfying the behavior, the assumption, the constraint of EPS that are a very reduced communication and an independence from the solver that is used. Okay, and so we don't want to change the normal behavior of EPS. We work pretty well for some problems, okay, but badly for some. So this is the only one equation that I put in a slide in my life. This is my maximum level of equation. So what does that mean? That is RTR, is the time you need to solve. So you are going to solve some problem and suddenly you are not able to make some progress and all your workers are not used. If all the workers are used, you just have to wait, okay? But suddenly you have a number of problems that are not solved, which is R, which is less than W, the number of workers. A here is a number of active work. So what you have here is the remaining time to solve the remaining problem after a decomposition, if you redecompose. But if you redecompose, you have new problem to solve. And this is the time to solve the part of that problem. And if everything is perfect, you can divide it by W, okay? You have W, it will be perfect. This is the time to redecompose your R subproblem. And here, this is the time for solving the R subproblem minus the time you have already spent, okay? So the time which we mean to spend if you don't recompose is this time. Okay, this is a nice formula. The problem is that almost everything is unknown. Okay? So we don't know precisely TR, not RTR, not DR. So it's very difficult to apply in practice an equation which is simple with 4 unknown variables. So the problem is that we are going to try to eliminate the variable. So in order to eliminate the variable, the first thing is that we are going to link this thing, which is the remaining time after decomposition, with these two things here, and saying that, okay, I need the total time minus a certain quantity of what I have already done, and the Q here can be appreciated. That is, I can estimate the part that I've already done in the search for solving the problem, and that I can avoid by doing something like a kind of no-good recording. And we observe that the decomposition time does not really change between the decomposition. So we can consider that this is constant. So we are going, so this is known now because this is the only thing that is known here with A and W. This is a time we have already spent. And so now we link that, so we obtain a new formula which is like that. And the problem is that in new formula, this is a nice formula, but I don't know TR. Okay, so what can I do? I can do something, is that I say, okay, so imagine now I'm trying to solve my problem, and after T unit of time, nothing changed. That is, I didn't solve any problem. So now I can make some progress because I know that TR is greater than that. And so this is the time that I spend for each active worker. So now I can say that, okay, if that is greater than that, and if that is greater than that, then I will know that TR is greater than that. So I have something like that after T unit of time, so I can decide the value of T. Then it may be worthwhile to already compute. So this is a bet. So in order to represent the bet, I'm going to put an alpha. Okay? Because the problem is that if I redecompose where I shouldn't have redecomposed, I lost some time. So alpha is the risk factor. Okay, so kind of no good recording to avoid the thing here. So we can compute the thing here, and we have a formula. So now if we apply this thing, what we discover. So here are some results, and what is important, this is a sequential time. We use 96 core exactly. And this is EPS, and this is EPSrd, which is with redecomposition. So what you can see first is that for this problem, I need 1,500 seconds and 3,000 seconds with 100 cores. Not really useful, okay? Not really efficient, okay? So you can have very strange behavior like this one. When this is short, it depends. Sometimes it's gain, sometimes it's lose. You have something like that. But here you can see that for some problems, this is not obvious. The factor is not always good here. For instance, for this one, the factor is not very good. And for some problem, is that it's difficult to obtain something like more than 25. And the overall result of EPSrd is that we improve almost everywhere, okay, and especially for hard problem. And for this one, for instance, we need now 200 seconds instead of 3,000. And so the factor, the mean, is now 40 for 96 core. This is a good factor that we are able to consider. And here we have 4.2. So this is these are geometric means. So these are a very good factor for EPSrd. So now if we look into details, we can have some information. A very interesting table is this table. Here we put the time of the decomposition. You can see that the time of the decomposition here is going to be increased for some problem, because in fact we really decompose several times. So this is before the first decomposition, and here this is the time that is spent when all the workers are active. That is the perfection, okay? And here this is the time that is spent when not all workers are active. And so what you discover is you don't redecompose here. For instance, you spend only 3 seconds when all workers are active. And then after 3 seconds, you spend 4,000 seconds without less than the number of core active. So here, wow, this is difficult. This is a difficult problem. Huh? And so here you can see that the total time, which is 4,000, is now divided by 10. And so we increase a lot the time which is spent when all the workers are active for difficult problems. Okay, and this is how we can gain some factor like that, and how, because we redecompose and split the problem into the difficult problem into some other problem. So now if we continue, if we look at the number of sub-problems per worker, I mentioned at the beginning that for EPS, it was between 30 and 300. And here we can see that this is the case. 10 is not enough most of the time. And, you know, we have some degradation like that are very bad. And sometimes this is the opposite. And, but you can see, so I don't remember if I took, I think that we took 100 of the time in the experiment, something like that. And for EPSrd, you can see that the minimum is better because we are ready to manage the bad load balancing by a redecomposition. Okay, and so here you can see the factor that we obtain between both. And another thing here, which is interesting for EPSrd, is the impact of the alpha value, that is the risk that you are ready to take. And another thing here for you is the number of redecompositions that is performed by the redecomposition mechanism. For sometimes there is no difference for the problem, no need to redecompose. But for problem, we can go up to 14 redecompositions. That is a lot. And a problem that was very, very difficult was this one. I think that we are part of the climate change to try to improve the solving of this problem. When a good action is to switch off our computer, you know, it was so much hard to do that. And so you can see the difference. Here, there is not a lot of difference. I think that we select 0.3 in general, and works pretty well. Not a lot of difference except for this one, which poses some problem. Okay. So if we try to avoid the recomposition, if we don't avoid some recomputation, because when you spend some time in solving a problem and when you redecompose, you can decide to try to avoid the part of the computation you have already done, or you don't do that. Okay. Does not gain a lot, but gain 20%. That's not bad, 20%, because 20% on the number of cores correspond to 8 cores. So this is not bad. And what we have also is that we have also shown, there is a table showing that EPSrd is much is more robust than EPS, and this is clear. Is that because the redecomposition introduced some robustness in some stability in the computation. Okay, so here in this talk, we focus on the parallel solving of the TSP problem with EPS. We identify 3 major issues: unstable decomposition, that is when I decompose more, it can take more time to solve the problem. Non-monotonic decomposition, when I have to decompose, it's difficult. The number of subproblems can be increased by the depth or can decrease and can change during the same decomposition step. And we observe extremely heterogeneous subproblems. And so EPSrd, which proposed to use the redecomposition, improve EPS by solving this issue. Okay. And we have shown that a small number of subproblems per worker lead to best result when you EPSrd, because the load balancing is managed by
do you know if there is a correlation between the gap, the optimality gap, and the difficulty of the problem?
What do you mean by the optimality gap? Because here we are very close to the optimality all the time.
You have the upper bound, even by linear gap, you said, and you have the lower bound of your CP model at that node.
Yeah.
So that's the gap between the two. I can imagine that if the gap is large, it will take more time for that problem.
That's interesting. No, we didn't look at that. Yeah.
One of the problems I've had at 100 cores is memory bandwidth. So although you've got 100 times the compute, when you're actually accessing memory, if you run 100 solvers, even independently parallel, they will run much slower. Do you have a way of dealing with that?
Okay, about the bandwidth, we have 2 things here. Is that we have a transmission of the problem, which when you have few times, for instance, few seconds, it can play a role. So something like 1 second or 2 seconds. We measure that because we have the number of integers that are transmitted. Because when we redecompose problems that are huge, we transfer some information. But globally, when you look at the times that is for difficult big problem like this one, it does not play very much, okay? Because it's, but for the small problem, it plays more. And then there is another thing about the memory is that when you consider our machine is in fact 4 machines, and each machine has 2 sockets, and so they share memory for 24 cores, okay? But what you learn once again is that if you want to be fast, you have to minimize the memory that is used by the solver, and the solver allocate everything as possible. So, for instance, we rewrite the Java allocator, of course, and we don't use a garbage collector in order to avoid the problem of the share memory that we can.